Hey you guys, this is Unit 3, Notes number 1, okay? So just to give you a little bit of an overview, in Unit 1, we focus on big idea number 1, which was limits, right? The concept of getting arbitrarily close to something but not exact, right? And then that kind of segued into well, what if we got arbitrarily close in regards to two different points? And, we were able to turn a secant line, take the 2 points, get them gradually closer to each other arbitrarily, eventually creating a tangent line, which we call an instantaneous rate of change, or the fancy word here is derivative, right? Which is big idea number 2. So in the next 2 units, what you guys are doing is you're learning a little bit more the application of what derivatives can do. So in Unit 2, you learned all the tricks, how you actually take the derivative. We were focusing a lot on the analytical, okay? Now we're going to focus a lot on the graphical, but as well as, well, what are the implications of a derivative and what can it do for us, right? So just think about that. Have that in the back of your mind. So here we go. Go ahead and copy down the FLT. Press play whenever you're ready. So given a function here, you're going to be able to explain the process to find something that we call absolute extremas, okay? Absolute extremas. And no, that's not a typo. It's extremas, okay? All right, here we go. So here, don't write it down. I'll highlight what I think you should write down. Here it says let f be defined on an interval I containing c, so some value c. So it says f of c is considered the minimum of f when f of c is less than or equal to f of x for all x and I. Let me explain this to you guys, okay? So at some x value c, okay? When you plug it into your function, you get f of c. So this right now is your y value. Okay, so they're saying that f of c, this particular y value, is considered the minimum or the lowest value when f of c, when this y value is less than or equal to all of the other y values. So it's the lowest y values out of all the other y values. Okay, that's how you guys read it, and that's how you interpret it. Make sure you guys understand this notation here. F of c less than or equal to f of x is fancy for minimum. Okay, absolute minimum. Similarly, so make sure that you guys write that highlight down. And feel free to add on to whatever you need to, okay, to help your understanding a little bit better. So same thing, if you have f of c and it turns out to be the maximum or the largest y value, then that means that y value is larger than all the other ones. Okay? Replay that a couple times. It's not super complex, but you want to make sure you understand the language here, okay? Okay, so second thing, so when you call something a minimum or a maximum, you can generalize it. You can call it extreme values or extremas. So if you want to generalize maximum or minimums, you just call them extremas, okay? Plural, if you have multiple extremas, you call it extremum. But that's basically it, okay? Today, we're learning two different types of extremas, okay? The first one, which we're going to focus a lot on, is the absolute minimum or maximum, okay? On the AP exam or in some problems in your book, they might use the word global. It's the same thing. They're synonyms, okay? Okay, so here we go. Here is a picture for you guys. I'm going to draw you guys a picture. Try that. There we go. Okay, So let's say we had a graph and we had a function that looks like this, okay? Try to draw it as similar as you can, okay? Okay. As close as you guys can. Okay. Now, what I want you to do, okay, probably using a different colored pencil or pen, I want you to tell me where the absolute highest point is and where the absolute lowest point is on this green graph. Okay? Okay, I'm going to have you guys pause here, so I'll rephrase the question. You're going to identify where the absolute maximum point is and the absolute minimum point. Press play when you're ready. Okay, so in this example, the absolute highest point happens to be right here. Okay. Now the absolute lowest minimum point happens to be right over here. Okay. So here's the question for you guys, all right? You know what? Let me draw another one. On the same graph so we don't have to draw the X and Y axis again. I'll use a different color. Whoops. Let's try that again. Okay. Looking at that purple graph, go ahead and label where the absolute highest point is and the absolute lowest point. Okay. Absolute max happens to be over here at this endpoint. And the absolute lowest happens to be at the other endpoint. Or absolute min, I should say. Okay. Here's one more, just to make sure that we really get it. I'll use pink here. Okay. Again, you're going to identify the highest and the lowest, aka the absolute max and the absolute min. Go ahead and do that. Press play when you're ready. Okay, the absolute lowest point happens to be right down here. Absolute highest point happens to be right up here. Or the absolute max, I should say. Okay, so where am I trying to get at, right? Okay, so here's some true or false questions, all right? And please answer it with me. True or false? The absolute maximum can occur at the end point. Okay? The absolute maximum can occur at the end point. Is that true or false? Okay. In that case, it's true because right here we have an absolute maximum occurring right at that endpoint. Okay. True or false? The absolute minimum can occur at an endpoint. Okay. That would be true as well. We have examples here where they occur at the endpoint. Okay. The absolute max can occur somewhere in between the two endpoints. Okay. The absolute maximum can occur somewhere in between the two endpoints. Okay, that happens to be true as well. Notice how the absolute maxes here occur somewhere in between. And lastly, the absolute minimum can occur somewhere in between the endpoints. Okay, and that would be true as well. Okay, so we're gonna write a statement down here, right? And then we're gonna revise it a lot. So we're gonna try to fit this all in one line, and we're gonna keep revising. Okay, absolute extremas can occur. Okay, we know that it could occur at endpoints. And somewhere in between. I don't have space, but you guys do. I should say or. And or. Okay? Okay. So let's dig in a little bit deeper here, okay? This whole somewhere in between. Where exactly in between do you guys notice here, okay? Take a look at... I'll get rid of some highlights so that you guys aren't confused. Okay, these three highlights right here are the ones that occur in between. Now, what do you notice in terms of where they occur in between? Is it just randomly anywhere, or is it somewhere in particular? Okay, pause, press play whenever you're ready. Okay, so here's what I want you to notice. And it's a little bit difficult because I can't interact with you guys, right? I noticed that it occurs in between, but specifically where the graph changes directions. So for instance, if we're looking at the green graph, okay, just the green one, the green graph starts to increase, and the moment it starts to change directions, that happens to be where the absolute extrema occurs. Same thing right here with this pink graph. The pink graph starts to increase, then decrease. But then the moment it changes directions here to increase, it had an absolute extrema there. As well as increasing here and then decreasing afterwards. So notice how an absolute max doesn't just occur like right here. Not in the middle of nowhere, right? Happens to be right where we change directions. Okay, so we're going to modify this a little bit, okay? So instead of saying somewhere in between, we're going to say where the graph changes directions. And we'll ditto everything here. Absolute extremes can occur at endpoints and or where the graph changes directions. We're going to come back to this, okay? Okay, so take a look here. If I draw you a graph, okay, will we always have an absolute max and an absolute min? That's the question I want you to think about as we go through a few examples here, okay? So take a look. And you guys can decide if you want to quickly sketch these graphs or not, okay? But take a look at this graph. It's x squared plus 1, okay? Now here, we have an absolute minimum right there and an absolute maximum. We have one of each. So here we have it, okay? Don't worry about this yellow rectangle. Now here, we have a minimum. But notice how this graph is drawn a little bit differently. It's open at the end, okay? So the thing is, some people will argue that the maximum is right there, okay? Which then I would ask you, what would the maximum value be, right? And if you argued 4.9, I would tell you that no, it's 4.99. And then someone else could argue, no, it's 4.999 or 4.99999, We can go on forever and ever here. So the thing is, there is no exact maximum value here because you could always get a little bit closer than the previous person. So here, notice how we don't have both extremas. Okay? Here, notice how we have a maximum, absolute highest point, but there is something wrong here. It's open at that 0. Okay? So some people might argue, well, you know what? The lowest value there is 1.01. And we can use the same argument. Someone else could say, no, the lowest value is 1.001 or 1.0001 and so on. So using that argument, in this picture, we don't have one of each. Okay? We don't have both absolute extremas. Now look at these 3 pictures. Okay? I'll go in order. Now, the first one on the upper left here, there's an absolute maximum right there and an absolute minimum right there. We have one of each. Okay? The one on the upper right here, we have an absolute max right there and an absolute minimum right at the end point. Okay? Now, this bottom one here, we happen to have a tie. Okay? Both these 2 values, okay, are equally as high. So here we could have multiple absolute extremas that they share the same y value, right? And then we happen to have an absolute minimum right there. Okay. So here's my question to you guys. Are we guaranteed one of each at least? Are we guaranteed, right? Think about that. You don't have to answer it now. Here are 2 more pictures. Now, I'm going through these very quickly, so you guys could go ahead and rewind to draw it if you guys want to, okay? We're just exploring here. So take a look at this upper right graph. Notice here, there's none, okay? Remember, someone might say that the absolute minimum has a value of 1.01, but again, we can make that argument of getting super close. Okay, same thing here. The absolute maximum is not right here because the graph keeps on going higher and higher and higher, and we can make that same argument too. So in this picture, we actually have none. Okay, we don't have any extremas. Let's take a look at this picture here. Okay, do we have an absolute highest and absolute lowest? Okay, pause here. Press play when you're ready, okay? We actually have an absolute minimum here. It's right there. Okay, but we don't have an absolute maximum. Okay, some of you may argue, well, you know what? It's this point right here. Okay, but I can argue with you that I could pick something a little bit higher than that. But then someone can argue that they could pick something higher than that, higher than that, higher than that, higher than that, and we could go on forever, okay, by getting arbitrarily closer. So here, although it looks like it, there is no absolute maximum. So we only have an absolute min. Okay? Okay. So here we go. When are we guaranteed one of each? This is our next existence theorem, okay? Number 2. I'll give you guys a second to write that down in a second, okay? The first one that we went over, the first existence theorem, okay, was called the intermediate value theorem. I want you guys to go ahead and pause and just quickly review what the intermediate value theorem is, okay? Go back to Unit 1, read it, and then refresh. Okay, so the intermediate value theorem, I gave you guys a birth height scenario, okay? If someone is born 19 inches tall and now they're currently 8 feet, right? You're guaranteed for this person to have hit every single inch and even every single fraction of an inch in between 19 inches and 8 feet. Okay? As long as the function was continuous on a closed interval. Okay? So take a look at here. When are we guaranteed extremas, or at least one of each? For instance, why did we have at least one of each in these 3 cases, but we didn't have at least one of each in this case or this case? I think those are the only 2. Okay? So when are we guaranteed it? So here you go. Here's existence theorem number 2. It's called the extreme value theorem, but I want you guys to just think of it as the extrema value theorem so that you can remember that extreme value theorem is really just referring to the absolute extremas, okay? Now, we call it the existence theorem number 2 because you're just trying to prove that it exists. We don't necessarily care where it happens for now, okay? We just need to be able to prove that you're guaranteed to have it. It's guaranteed to exist, okay? So here are the stipulations, okay? The condition is as long as your function is continuous on a closed interval. So notice how it has the same condition as IVT. So this is very easy to remember. So if a function is continuous on a closed interval, the intermediate value theorem is going to work as well as the extreme value theorem, okay? Now, this is a very informal way of writing it. If f is continuous on a closed interval from a to b, then you're guaranteed one of each. Okay? This is a very informal way of writing it. So let's take a look. What is continuous? So let's refresh, right? Informally, continuous means that you don't have to lift up your pencil, right? Okay? So look, take a look at the first few examples that I had, okay? Whether I drew the green graph, the purple graph, or the pink graph, notice how I never lifted up my pencil. And I don't think you guys did either, right? And that's why we were guaranteed at least one of each here. Now, take a look at this one. If I were to draw this graph, I would never have to lift up my pencil, which is why I had to have one of each. Now, remember, that's not a good enough justification. Remember, continuity follows the 3 conditions, but we'll get to that later, okay? So we're just being very informal about it for now, just to understand when it works and when it doesn't work. Now here, is this continuous on a closed interval, right? It looks continuous, but it's not continuous on a closed interval. Notice how the intervals are not closed. They're actually both open here, which is the reason why we didn't have one of each. Okay? Let's take a look at a couple more. Now here, why didn't we have one of each, right? Pause here. Think about how you would answer this question. Why did we not have one of each here? Press play when you're ready. We didn't have one of each here because this function was not continuous. Notice how there's a breakage right there. So we had to eventually lift up our pencil, which is the reason why we don't have one of each. Okay? You're not guaranteed that. Now all of these 3 pink graphs, notice how they are all continuous, and they are all continuous on a closed interval, meaning the endpoints are closed. Closed intervals. Okay, the endpoints are closed. And that guaranteed us at least one of each. Now, even though this has 2, remember the word is at least one of each, okay? Now here, take a look at this one, okay? Why did we not have any here? It looks continuous, right? But the thing is it continuous on a closed interval? right? That's where it kind of fell open, all right? This is continuous on an open interval, but not a closed interval, which is the reason why we couldn't have any extremas here, all right? Now this last one, why didn't we have one of each, right? We didn't have one of each here because the function wasn't even continuous. There's a breakage right there at 1. You had to lift up your pencil there, but you would just say that the function was not continuous, right? And there you have it. So this is it in a nutshell, all right? If your function is continuous on a closed interval, then you're guaranteed one of each, all right? Let's keep going. So, here's a picture for you guys. That's the sloppiest graph I've ever seen. Okay. You could always get away with it by saying not to scale. All right, here we go. Something that I want you guys to kind of visualize here. All right. I'll even close it. Okay. Same idea here. All right. I'm going to ask you guys to identify your absolute extremas. Okay. Put a dot there, put a point there, wherever you think the absolute extremas are. And press play when you're ready. Okay. Now, if I'm looking at this graph literally, the absolute max should be here, because it's the highest point. And this one is the lower one. Okay, that one looks close, but it's not quite as low as that other point here. Okay, they happen to occur somewhere in between, but remember, where do we mean somewhere in between? Where the graph changes directions, right? And is that true here? Okay, notice how this is where the graph changes directions. So we're going to take that one step further. Okay. Okay, now we're going to reintroduce the tangent line. Okay. Now, you don't know enough yet in terms of the tangent line, but all you do know is that a tangent line is a line that intersects a curve at one point. Okay. Here's the thing. You know, if you had a secant line, okay, and you're making these 2 points closer and closer to each other. So if I'm scooting this point over here, eventually that tangent line, I'll draw it in pink, will look a little bit like this. Okay? So there is a certain way that you draw tangent lines. You can't just say, all right, that is a tangent line because it intersects the curve once. By definition, a tangent line is when you have a secant line where the 2 points are getting arbitrarily closer to each other to the point where they overlap. So when they do that, and I'll introduce it to you now, we call it concavity, okay? Pretty much, your tangent lines always have to be outside of your curve, okay? And outside is relative here, okay? So for instance, if I had a point here and I want to draw a tangent line, it would have to be outside of your curve, okay? But it gets a little weird because what if you keep going, right? Then your tangent lines are outside, but the outside is relative based on how it's curved. We call that concavity. But notice all of these purple tangent lines are kind of hugging the graph. So you can't just say that this is a tangent line because it intersects once. So make sure that you guys don't do that there, okay? All right, so here's what I want you to do. Let me erase this real quick. Okay. If you were to draw a tangent line at the absolute extremas here, what would it look like? Okay, do this in pencil in case you make a mistake, but give it a guess. I definitely want you to give it a guess. At these absolute extremos, these 2 red points right here, how would the tangent line look like there? Press play when you're ready. Okay, so here, the absolute extrema if you were to have a point right there, your tangent line should be like that, okay? To the point where it's horizontal. Same thing here. Okay, so here's what we've done, all right? We noticed something a little bit more. We noticed that the tangent lines are both the same in terms of its orientation. Specifically, we know that these tangent lines are horizontal at these absolute extremas, okay? So we're going to go back real quick. Go back to the beginning of your notes here. We're going to modify this a little bit more. So we said absolute extremas can occur at endpoints and or where the graph changes directions. We're going to do one better. We're going to say that this is where the tangent line is horizontal. Okay, ditto, ditto. So we're slowly revising the statement to see where it leads us, okay? All right, so look, we can go a little bit further. Now here we go. What do you guys know about horizontal tangent lines? Okay, really pause here and think about it. It's not too obvious, but think about the implications of a horizontal tangent line. Okay, so we know that horizontal tangent lines, okay, have a slope of 0 because it's horizontal. Okay, now what notation do we use to start discussing the slope of a tangent line? Right? So if we want to start talking about the slope of a tangent line, if you guys think about the entire unit in Unit 2, when we want to talk about the slope of a tangent line, we talk about derivatives. So horizontal tangent lines is basically saying when the derivative is 0. Okay? Make sure you guys understand that. When the derivative is 0. So take a look. We're going to cross this out one more time. And or where f prime is equal to 0. I'm actually going to put f prime of c here. I'll talk more about that later. Okay, that's pretty much where the slope of the tangent line is horizontal or 0. Okay, all right, here we go. Now, the second type of extrema, you see it right here. They're called relative extrema, aka local extrema. Okay, so in the same picture, I'm actually going to locate all of the local extremas. You might have seen this in pre-cal or in integrated math 3, but don't worry if you haven't. So when you think of the word local, you think of the word or the phrase in the area. When you want to go eat local, right? You want to eat somewhere in the area or somewhere nearby. Okay, so here's how this works. Local extremas is the highest and the lowest, the max and the min, but only locally. So for instance, if I'm only looking in this area right here, and you guys shouldn't box it, all right? If I'm only looking inside this blue square, the lowest point in that blue square is right there. So I can call that my local extrema or my local min. It definitely isn't the absolute minimum, but locally it's a minimum. Okay? Same thing here. In this area, that is my local max, because in that square, in that blue square locally, that is the highest point. Okay? Same thing here. In that blue square, that happens to be a local max, which is coincidentally also our absolute max. Same thing here. If we look inside that square only, that right there is a local minimum. And same thing here, locally, that is the highest point, so we call that local max. So take a look. Your absolute extremas can occur at the endpoints, right? Or somewhere in between. And then we changed our somewhere in between to wherever they changed directions. And then we changed wherever they change directions to wherever they have a horizontal tangent line. And instead of horizontal tangent line, the implications is pretty much where the derivative comes out to 0. But we're going to change it even more, okay? This is pretty much where a local extrema can occur. Notice how the local extremas, okay, could land on an absolute extrema. So we're going to go back and change that as well. Okay. Okay. Ditto, ditto. Where there is a local extrema. Okay. So here's the thing. Where are we trying to get at here, right? We keep revising this statement. So let's take a look. Let's explore. Oh no, I didn't erase it. Okay, imagine you didn't look at that. Okay, here's example 1. You'll notice that there's a lot of exploration here, so be very patient with it, all right? Okay, here's a little bit of a refresher, a throwback to Unit 2. Go ahead and write this down. Okay, here's what I want you to do. I want you to find the value of the derivative at this point. Okay, you guys know how to do this. So pause. If you don't, look back at your notes if you need to, but find the derivative at this point. Okay, here we go. So if this is f of x, well, first maybe I would want to distribute the 9 at the top just so that there's no confusion. But I would definitely use the quotient rule here. I can't seem to avoid it to make it look easier. So quotient rule, we start with the bottom times derivative of the top minus the top times derivative of the bottom, all over bottom squared. Okay, the derivative of the top is 18x. The derivative of the bottom is 3x squared. If you're not sure how I got that, check in with me or check in with a peer, okay? Okay, so here I have the derivative. I need to evaluate it at 3, 2. Okay, so go ahead and plug and chug here and press play when you're ready. Okay, now if you plug this in, you should have gotten 0. Okay, now if you didn't get 0, double check your work. Okay, double check your work. Now what the heck, right? So let's take a look at it graphically. So you guys are taking off your analytical hat and you're putting on your graphical hat right now. What's the connection, right? Remember, you guys can't rely on just one hat here. You have to switch back and forth to the 3 different hats. So we found the derivative. Remember what derivative means. We found the slope of the tangent line at this point. So let's take a look at what that looks like with the graph here. So here is f of x, the graph, and notice at 3 comma 2, that happens to be a local max, or a relative max if you want to call it that. Now if you want to draw a tangent line there, it would look like it's horizontal, which implies that we have a derivative that's equal to 0. Hopefully you guys are making the connection here, okay? We notice that every time there's a local max or local min, the derivative comes out to 0. So we might be onto something here. So here's what we do. Here's one more for you guys, okay? I'm going to give you this function, and I'm going to ask you to find the derivative at that point, okay? Go ahead and do that real quick. We can call this part B if you want. Okay, now here, f prime of x would be 3x squared. We would evaluate it at 0, 0. That would just give me 0. So what does that imply, right? When the derivative is 0. Now some of you are saying, well, there's a local extrema there. So here's the thing. If you were to graph x cubed, which you guys should know how to sketch, but if you don't, learn it. Okay? X cubed looks a little bit like this. If you notice, okay, if you notice right there, it's a little bit weird, right? Because how can you draw that tangent line? Actually, let me fix this graph a little bit. It's a little bit flatter. Maybe a little bit like this. Okay? Now, because I can't draw it perfectly, okay, it looks a little bit different, but if you were to zoom in there, that slope is 0. But it goes against what we've been talking about here. Okay, let me review real quick. You know, I'll copy paste this so that we don't have to go back and forth. We have this right here. Okay. So we started crossing out statements that were equivalent to make them a little bit more specific. So here we found out that this is where the derivative is 0. The tangent line is horizontal there. It is somewhere in between. But is this where the graph changes directions? If you draw this cubic function, you notice that it's constantly increasing, right? So what the heck? And also, is this where I have a local extrema? Is 0, 0 a local max or a local min there? Notice how that is neither, because there's always something higher than it or lower than it. So it's neither local extrema. Okay? Okay, so here's the thing. We have to go back and revise this a little bit more. Okay? So, I'll open up a new page. So here, we introduce something called a critical number. All right? We introduce something called a critical number. A critical number, you guys, if f is a function, okay, then c is a critical number such that f prime of c equals 0 or f prime of c is undefined. Okay, that's the very fancy term for it, right? Okay, so here's how you guys need to think of critical numbers. So every time I ask you, okay, what a critical number is, here's what you're going to say. A critical number has the potential of being a local extrema. Okay? A critical number is not a local extrema, but it has the potential of being a local extrema. So here's what I mean by that. For instance, this example here that we just did, we found out that at 0, the derivative came out to 0. So that should be a critical number. But it didn't necessarily give us a local extrema. Okay? But here, when I took the derivative and I plugged in the point, I got 0. So at 3, 2, that's my critical number. In this example, I actually did get a local extrema. So you're not always guaranteed it, right? So that's why we squeeze in the word potential. All right? Okay, so we go back to the very beginning. We're going to cross this out one more time. Okay, here's what we're going to say. Absolute extremas can occur at the endpoints and or at a critical number. Okay, it could occur there. Okay, that's where the or part comes in, okay? So it could occur at the endpoints or at some critical number. All right? So a critical number is basically where the derivative is 0. All right? Okay. So here we go. Same thing here. Just to kind of like make sure that we understand the problem. Here's part C. Okay, go ahead and find the derivative or the slope of the tangent line at these 2 points, or these 2 x values, I should say. Press play whenever you're ready. So here, the derivative of sine is cosine x. Okay, so the derivative at pi over 2 should be the cosine of pi over 2, and the derivative at 3 pi over 2 is the cosine of 3 pi over 2. Okay, you guys got to practice your trig values, okay? For those that I spoke to last year, the one thing that I asked for was that you guys know your trig ratios, okay? Cosine of pi over 2 is at 0, as well as 3 pi over 2, okay? Notice how the derivative is equal to 0. When the derivative is equal to 0, we call those critical numbers. Critical numbers have the potential of being a local extrema, okay? So take a look. Here's the picture graphically so you can see it. If you were to draw a tangent line there, notice how they're both horizontal, and they're actually local extremas, okay? All right, where am I getting at? Let's practice. Here's the big meat, okay? The big meat of the lesson here today. Go ahead and write it down. Notice how you will need your calculator, so I'm going to be going through that. And press play when you're ready. Okay. Now, what throws people off the most is the wording on the AP exam. Obviously, when you see it for the first time, it gets confusing, but with a lot of exposure and a lot of breaking things down, I can help you guys out there, okay? Here, they say find the extrema, okay? But don't you guys know 2 different types of extremas? Isn't there a local and an absolute, right? Isn't there a global or a relative extrema? So here, they didn't really tell you what, okay? But because because they gave us a closed interval, it's implied that we're looking for an absolute. Make sure you guys understand that. Okay? All right, so here we go. Absolute extremas can occur where? Okay, review back if you need to. Absolute extremas can occur at the endpoints or at a critical number, right? What are my endpoints here? My endpoints are the endpoints of the interval, okay? So, here's what we do. I'm just going to put it right here. I'm going to make a table. That's the straightest, most horizontal line I've seen. Okay, what we want to do is we want to try to find out where, at what x value, will f of x give me the highest and the lowest point, okay? So we know that it could occur at the endpoint, so I'm going to put -1 and 2. But notice how I left some space in between. Remember, what could happen in between, right? The absolute extremas could occur at a critical number, which is what I'm saving space for. All right, so here we go. We're going to find a critical number. So what we do is we take the derivative. So go ahead and do that, you guys. So if f of x is 3x to the fourth minus 4x cubed, the derivative should be 12x cubed minus 12x squared. Okay? What we're going to do right now, okay, is because since we don't have points, we have to find it. What we're going to do is we're going to purposely set the derivative equal to 0. Okay? Because what we're doing here is we're finding our critical numbers. Okay, so if we're finding critical numbers, we're setting the derivative equal to 0. We're not setting x equal to 0, okay? So here is a little bit of algebra. You're going to have to factor out the GCF here. We can factor out a 12x squared. If I take that out, there's going to be a x minus a 1 left. And here, using the zero product property, 12x squared can equal 0, or x minus 1 can equal 0. All right? So if you solve this here, x is going to come out to 0, or x is going to come out to 1. Now, I didn't show the steps in between, but if you don't know what happened, just let me know. I'll go through with it with you, okay? So here's a question for you guys. What do these two values represent? Okay? Because it's very easy sometimes when we're so into the problem, we forget what everything represents. What did we just find, right? So I'll note it again. We just found our critical numbers. We have 0 and 1 as a critical number. Okay? It has the potential of being a local extrema. All right? So here we go. Is 0 and 1 somewhere in between -1 and 2? Yes. So if you're starting at -1 and you walk all the way towards 2, eventually you're going to cross 0 and 1. Now, sometimes you may get a critical number that's not in your interval, in which case you just ignore it, okay? So here's what we do. We need to plug in all of these values here into your function, okay? And you could do one by one, or we could use the functionality of the table. So here's what you guys do. First off, go ahead and reset your calculator, okay? So second plus 712. Second plus 712. Okay, first thing you want to do, you're going to go ahead and go to y equals, and go ahead and type in your function, f of x equals 3x to the fourth minus 4x cubed. Okay, so what you want to do now is go to table set. So right above window is table set. So we're going to go to table set, and I'll do this with you guys. Let me type this in real quick. 3. Okay, so when you go to table set, so second and then window, you should see two words, independent and dependent. You want to go ahead and change independent to ask. So hover over the ask and then press enter, and it should bold it. So now when you go to second and graph, you're going to access your table here, okay? You should see a blank table. What I'm going to do is I'm going to type in these four values. So -1, 0, 1, and 2. Okay, and if you did that correctly, you should have gotten 7, 0, -1, and 16. Okay, now before you move on, if you didn't get that, definitely talk to a peer or talk to me to troubleshoot. Okay, so when you get to this level of math, we don't want to spend all this time, if this was algebra 1 or algebra 2, they would make you go f of -1 equals 3 times -1 to the 4th power minus 4 times -1 to the 3rd. And then you have to solve it. And then you go f of 0 equals 3 times 0 to the 4th minus 4 times 0 to the 3rd power. You would have to do everything by hand. But with calculus, we don't care about the baby work. Okay? So take a look here. Okay? Which y value is the largest? Okay, so you want to be very careful in how you write this, okay? The absolute maximum value is 7. Okay? The absolute maximum occurs at x equals -1. Okay? When they ask you where it occurs, it's the x value. If they ask you what the value is, you're looking at the y. Okay? So go ahead and do the same thing for the minimum value and as well as where it occurs. Okay? Okay, the absolute minimum value is -1. The absolute minimum occurs at x equals 1. Okay? And that's it. Right? So look, absolute extremas can occur. I'll highlight in blue here. Yeah, that's a good color. Okay. First, okay, absolute extremas can occur at the endpoint. So right away, you make a table. Okay? But you leave some space for your critical numbers, which you'll find, and you'll slap them in there if they fit. Then you make a table on your calculator to find all the y values, and then you make your conclusion. All right? Now, we went through this for a very long time so that you guys could really understand the process of it, okay? So this is the actual picture. So take a look. The absolute lowest point or lowest value was -1, like we said, and it occurred at x equals 1. And the absolute maximum value was 16, and it occurred at x equals 2. Oh, why did I put 7? Why didn't you guys stop me? Just kidding. You guys can't stop me. Oh, I didn't see the 16. Okay, the absolute maximum value, you guys are probably freaking out right now. The absolute maximum value is 16, and it occurs at x equals 2. Whoops. Okay? But nevertheless, the same process. Okay? So you found that analytically, but here it is graphically. Let's try another one. Okay? Here's part B. Try it out. Go as far as you can. And then press play whenever you need to. Okay. So here, right away I see an interval. It's written in inequality notation, but that's not going to scare me. So this is basically -1/2 to 4 closed, okay? So -1/2 I'm going to put in. 4 I'm going to put in. I'm saving space for my critical numbers. So the derivative here is 3x squared minus 6x. I set my derivative to equal 0 because that's what a critical number is. So then I got to solve, so I notice I could factor out a 3x. That'll leave x minus 2. If you solve that accurately, x should equal 0 and 2. Okay? I pay attention. I make sure, does 0 and 2 fit inside of my interval? Yes, it does. So I'm going to put that in there, 0 and 2. I'm going to go back to my graph. So what I'm going to do is I'm going to go ahead and go back to my y equals because now I have a new function. So I'm going to type out x to the third minus 3x squared plus 1. Okay, now you don't need to go to table set because you've already changed it. Now, if you reset your calculator, you're going to have to go back and do it, okay? So I'm going to go back to my table, and I am going to delete the previous 4 values that I had on there. I'm going to put negative 1/2. You could put negative 0.5 if you want. 0, 2, and 4. Okay, I'm going to write this down for you. I have 0.125, 1, negative 3, and 17. Okay, so my conclusion is the absolute max value is 17. Absolute max occurs at x equals 4. Absolute min value is negative 3. Absolute min occurs at x equals 2. There you have it. Okay. Let's keep going. Here's part C. Try this one out and press play when you're ready. Okay, so same thing here. We know it's absolute extrema because there is an interval, so we know it's absolute. And also because you guys haven't learned how to find locals yet. Okay, so x, f of x is going to go in here. All right, I know it could occur at the endpoints, negative 1 and 3, but I left the space for critical numbers, which is where the derivative is 0. But the derivative here is 2 minus 3 times 2/3 x to the negative 1/3. Okay, that comes out to 2 minus 2 over x to the 1/3. Okay, so here's the thing. What you guys have to do is, well, how do we subtract fractions? We need common denominators. So we're going to need an x to the 1/3 here, x to the 1/3 here. That'll give me 2x to the 1/3 minus 2 all over x to the 1/3 equal to 0. So I kind of lied to you guys, all right? So if we go all the way back to what a critical number is, a critical number is where the derivative is 0 or undefined. Most people neglect the undefined part. And I neglected it in the previous two because the only way you can get undefined values is if you have a fraction. In the last two problems, we didn't have a fraction, so we didn't worry about it. So here's what you do. Basically, if you want a fraction to go to 0, you set your numerator equal to 0. If you want it to be undefined, you set your denominator equal to 0. Make sure you understand that before we move on, okay? So here on the right side, to get rid of a cube root, I'll just cube both sides. So x equals 0, okay? Now over here, 2x to the 1/3 equals 2 if I bring over the 2. If I divide by the 2, I'll get a 1. And if I cubed both sides to get rid of the cube root, x will equal 1. Okay, so here I have two values, 0 and 1. Does 0 and 1 fit in between my interval? It does. Now again, if you found critical numbers that's outside of your interval, you don't use it, okay? Because you're only worrying about the highest and the lowest within that interval. Okay, so here we go again. That's the tough part. The easy part is just letting the calculator do all the work. Okay, so I'm going to go ahead and type out my new function, 2x minus 3x to the 2/3. Make sure that your 2/3 is floating in the exponent, okay? Okay, cool. Let's go to table. Let's get rid of our values. I'm going to put in -1, 0, 1, and 3. So I get -5, 0, -1, and -0.24. Okay, and from there, you guys can make your statement, okay? I don't want to write it, but you guys should. The absolute maximum value is 0, and it occurs at x equals 0. The absolute minimum is -5, and it occurs at x equals -1. All right? And there's your picture to kind of verify that. Okay. This is my last one. Yay. All right, here we go. Part D. Try this one here. And press play when you're all done or if you need help. Okay. So, again, I know the absolute extremas can occur at the endpoints. So, -2 and 1. I left space for my critical numbers. So I need to find my derivative, which is 12x squared minus 24x. Okay. And I want to set my derivative equal to 0 because that's the definition of a critical number. I can factor out a 12x, which gives me x minus 2 left on the inside, which then tells me that x equals 0 and then x equals 2. Okay. And then I take a look, is 0 and 2 inside my interval? Well, if I'm going from -2 to 1, the only number that fits is 0. 2 is not in the interval. So what do? I ignore it. You don't use it. One less of a number for you to use. Okay? So I let the computer, I let the calculator do all the hard work. 4x cubed minus 12x squared plus the 7. I go to my table. I get rid of my old values. Plug in -2, 0, and 1. So I get -73 here. I get 7, and I get -1. Okay? From there, I know that my absolute maximum value is 7, and my absolute max occurs at x equals 0. My absolute minimum value is -73, and it occurs at x equals -2. And that's it. Okay? So we did learn about local extremas in general, but more in depth, we're going to find out how do we actually find local extremas in the next lesson, okay? So today, you found out the process to finding absolute extremas. So before you close out, you guys, I want you to write down the steps, okay? Now, I said it over and over throughout the lesson, but I want to make sure that you guys understand. So what we did was we created a table, okay? And I remind myself, I say absolute extremas can occur at the endpoints. So right now what you're doing is you're putting down the 2x values, and then you leave some space for the critical numbers, which is where the derivative is 0 or undefined. If the critical numbers are inside the interval, then you include it. Then you use your calculator to spit out the y values. And maybe make a note about what the difference with value and where it occurs is, okay? Make sure that you guys are formulating your thoughts before you close out, because that was a lot to absorb. So it's helpful to jot down your thoughts there, okay? But if you have any questions, let me know.